Good morning, everyone. So welcome back to QX01, Introduction to Quantum Information and Associated Technologies. So let's have a look at the final program for the next few weeks. So there were some changes made. Hopefully they are the last changes, although I'm not quite sure yet. So today, this is today, so lecture number 10. There's just a slight thing we haven't finished yet on the no cloning theorem that we're going to finish. And then today will be only 1 hour to compensate to the other hour that we did last time. And today it will be on what I call thoughts regarding the Schrodinger equation, or how to relate to quantum technologies, so a bit of physics for once. And then in the next few weeks, if all goes well, then it will not be me. So it will be only people from various places. So there are some changes. So next week it's in red and black because supposedly there's supposed to be no lecture, but there might be one. I'm not 100% sure yet. In any case, none of those most likely will be live anyway. It will be live for the UTT students, but then it will be put on YouTube afterwards. So this one is not completely confirmed. This one is confirmed the week after on quantum sensors, but this one will not be available on YouTube at all, on the other hand. And then the other two are also confirmed. So Introduction to Quantum Learning Machine, which is given by the... so quantum sensors will be given by the company, French company Thales. For this part, which is not sure, is the computing institute, French computing institute called INRIA. The Introduction to Quantum Learning Machine, which is the QLM machine that is sold by the company Atos, will be done by someone from Atos on the 8th of June. And then the last lecture will be on the 15th of June. And this will be a lecture on the various quantum technologies that we haven't touched upon. So during all the lectures, I talked about photonic qubits and spin qubits, but I haven't talked about superconducting qubits or ion trap qubits and other systems, and this will be touched upon during this lecture. And this will be given by a visiting professor from the Polytechnical University of Cartagena in Spain. And this is a bit special for us because this university is actually a partner university in our European University of Technology project that we have together. And it will be the first lecture given within that framework. So that's interesting. Which means that potentially today is the last day where I'll be speaking. Afterwards, it won't be me. And yeah, again, so those, everything will be, though these two will be available on YouTube, not live. This one will not be. And this one is not 100% sure yet that it will occur, but more, especially for the UTT students, more information to come. Right. So for today, so only 1 hour, but you will see that I will need that to talk about the topics I want to cover. So we'll just finish briefly the no cloning theorem that we talked about last time. You remember I said there are two demos to prove that theorem, and we only saw the first one, and I'll detail the second one. I mean, it's very simple as well. And then the rest of today will be on what I call thoughts on the Schrodinger equation, and what I should add is related to quantum technologies. And then within the quantum algorithm, there should be a part 2, as I said, which will be on Grover's algorithm, but also there should be also the Bernstein-Vazirani algorithm, hopefully given by our colleague from INRIA, and hopefully next week. But this is not 100% sure yet. Right. So the no cloning theorem, and just a quick reminder. So the idea is that we want to see whether we can have a machine, a cloning machine, where you put a qubit, a quantum state in, and you make a perfect clone of it out of it with this machine. You've got now two qubits or two systems with the same wave function psi. And quantum mechanics tells you that there is no such machine. Just doesn't exist. Okay, so you may be able to do it with sheep, but in a way, what quantum mechanics tells you is that Dolly's clone is actually not a clone as such, is also a proper sheep of her own. And for that, there are two proofs. So one we saw last time, and they are fairly simple. So the first proof is to use two different states and to use the inner product. So we did that already. The idea is to use. The idea is to go from the postulate that there is such a machine, that we have a unitary matrix, a unitary operator that will take this quantum state and clone phi into another phi, so we have two copies of it. And then we saw that actually when we do that, that leads to contradiction, because at the end what we ended with is when we took the inner product, or the scalar product, phi psi, then we end up with phi psi equals phi psi squared. And that's fine, but the only possibility for this equality to be true always is that so if you have x squared equals x, can only be true if x equals 0 or 1. So this scalar product can only be 0 or 1, and clearly it cannot be if I take, say, qubit 0 in superposition of 0 plus 1, then I will not find 0 or 1. So as this is not true, then the beginning wasn't true, the assumption, the first assumption wasn't true, and therefore there is no such unitary transformation, unitary operator that can clone a quantum state. The second demonstration is even easier in a way, is to use the linearity of quantum mechanics. So let's write this down. So again, we start from our state that we want to clone, and we want to clone it to this state. So for that, we use our cloning machine, which we model by a unitary operator that will transform this state into, well, this one, where now we made a copy of the psi state onto the 0 state. And of course, this is not possible. So how is that not possible? So for that, we will take the fact that a qubit can be written as a superposition of 0 and 1. Okay. So with two coefficients a and b. So now if we do that, so now we can take the tensor product of these two. Okay. And if we do that, that means that we have the tensor product of A0 plus B1, tensor product of A0 plus B1, and that gives us so A squared of 0, 0 plus AB of 0, 1 plus BA of 1, 0 plus B squared of 1, 1. Okay. And now I said, okay, well, let's let's start from that. So now we looked at this side. Let's look at this side. So this side would be that we want to clone A0 plus B1 tensor product with 0. And so if we do that, that means that basically, so we have the tensor product, so we have 0, 0, and 1, 0. But if I want to clone 0, so that would give me the state 0, so that's fine. I don't have to change that. So I've got A of 0, 0. I don't have to change that. But the other one would be B1, 0, but I want to clone that, so I want to make a copy of 1. So I would have plus B of 1, 1. Okay? So if I start from this state, tensor product with that, I end up with A, so I can do it. That would be A0, 0 plus B1, 0. And I want to clone that. That means I want to have on this wave function, on this qubit, the same as this one. So here is already the case. That's fine. Here is not, so I have to swap it. I have to change it through my machine so that I end up with this state here. And clearly, this state is different than this one. Okay, and it's supposed to be the same because I'm supposed to go from here to here, find this result, or to go from here to here and find the same result. But I'm not finding this. So the assumption is wrong. There is no such thing as a unitary operation that can clone a qubit or a wave function in general. Okay. So that's it. In few lines, this is it. The no cloning theorem tells you that you cannot make a copy. You cannot make a copy of a quantum state, or not a perfect copy. And that is very important, for instance, in quantum cryptography, in quantum key distribution, because you can use that in order to make sure that if someone tries to tap the line, if an eavesdropper trying to listen to the conversation, measure it and then send it back, then this person will measure and then send the results and will collapse the wave function, therefore change the quantum state, and therefore cannot make a copy of it, or perfect copy, and will send something wrong that on the other side, Bob or Alice or whoever is going to see that the state has changed. Okay? And that also part of the reason why quantum key distribution has its security from is the fact that this applies, okay? As opposed to classical cryptography where, you know, if I give you a CD-ROM, you make a copy of it, you give me back the CD-ROM, I have no idea that you made a copy of it, and I cannot tell that you did. Here, first of all, you can't do it, and second of all, even if you try, they will see that you tried. Right. So you can see the no cloning theorem we've been talking about since the first lecture. Of course, there is some math involved that's needed in order to make the proof. But you can see that in only a few lines, there are two proofs, and in only a few lines, you have the result. Okay, all you need is a bit of math, but afterwards, it's very simple. Right. So that's it for this part. So now, for today, I want to talk about what I call thoughts on the Schrodinger equation, because this is something that we haven't talked about so much. And the reason being that Schrodinger equation is really, if you want to do quantum physics, quantum mechanics, and quantum technologies. This is different. Having said that, what quantum technologies, in a way, takes for granted is the fact that you know your quantum system and you already solved it through the Schrodinger equation, or that you use quantum technology to solve it. So I thought at this point it would be interesting to give you some examples, some physical examples that we use in quantum mechanics, and to show you that some of them are useful for quantum mechanics and less so for quantum technologies, although this is debatable. And some are directly relevant for quantum technologies, and we already saw some examples like the electron spin, for instance, which I'll come back to it. So, Schrodinger equation. So, Schrodinger equation predicts the energy state and the Eigen wave function, or the Eigen values. So, Eigen, as in French, is valeur propre and vecteur propre, so les fonctions propres of the system. So this is the Schrodinger equation in two different notations. So this is in sort of standard notation, non-using Hilbert space in bracket notation. So I h bar, derivative of time of the wave function, equals the operator h times the wave function again. Well, not times, but applied to the wave function. And I have the equivalent in bracket notation, where the Hamiltonian in this case would be a matrix and the wave function is a ket. And in general, so the Hamiltonian, so it's a classical mechanics concept, but that transposes very well into quantum mechanics because it's a more general concept. And the Hamiltonian is the sum of two terms, is the sum of the kinetic energy and the potential energy of the system. So in a way, what the Hamiltonian is the total mechanical energy of the system. Except that now, using the Schrodinger equation and the Hilbert space in bracket formalism, this Hamiltonian here is actually an operator that leads to, which is an observable, which leads to measurements result that you find when you're trying to find the energy accessible of your system. So what you want to do is to resolve this equation. Okay, so in quantum physics, quantum mechanics, this is the first thing you have to do. So there is another version of the Schrodinger equation, which is this one, which is h psi equals e psi. So it's the same thing, except that this one is the so-called time-independent Schrodinger equation. And so let's have a look at this. And this is very important because it makes calculation easier because it allows us to remove the time from the equation in a way. So the idea is to assume that the total wave function, let's work in 1D along x 1D, that this wave function is the product of, let's write it like this, it's the product of a function depending on time and a function depending on the space only. So if I do that, if I put this into my Schrodinger equation, so like this, what I can do is I can, I can replace it by f in t, and I can make sure that all dependence on time is in one side and all dependence in space is in one side. And at the end, I end up with this equation. Okay, so I just rewrite this. In fact, well, let's do it. Well, that's fine. So, right, so I've got psi, and then derivative of time of f only, because only f is dependent on time, equals h of phi and f. I can take psi and put it the other side, and I can also take f, put it out, and then move it on the other side as well. So the reason why I can do that, normally I can't do that, because you remember that the Hamiltonian with the hat on top is an operator, is a matrix. So it has to be applied to something. So that means that I can't, this something here, I can't just swap it. I can't just say, oh, h psi equals psi h. No, that would be wrong. So in order to take f out, I can only do that if I assume that the Hamiltonian is not depending on time. Okay, so h is actually a function of x, but not so much on time. And the reason for that is because it's what we call the principle of ergodicity, which seems fair. It tells you that if I take the energy level of the hydrogen atom, for instance, which we are going to do, these energy levels are quantized, and these energy levels, whether I do the experiment today, tomorrow, or in 100 years, will be the same. So they do not depend on time. Although that's debatable, some people say that they are, because some constants actually are not constants. Maybe h bar actually has a dependence on time, but let's assume that this is a very long time, or that the change is very, very small. So that means that whether you do the experiment today or next week, you will find the same result. So there is no dependence on time. So I can write this as being like this. Then in this case, I can rewrite this equation, and I would have I h bar 1 over f df dt equals 1 psi h bar psi. And now what I have is, on one side of the equation, something that only depends on time, and on the other side, something that only depends on space, x in this particular case. And the only possibility that a function, a side depending on time is equal to a side depending on space, is that both of them are either 0 or, more general, equal to a constant, which we will call E. And it's an energy, because it's, you can see, it's the dimension of this constant has to be an energy. And then here we go. Because now we end up with something like, so if I look at this side, I've got h psi equals e psi, and that's the time-independent Schrodinger equation. So in standard notation or in bracket notation. And as for the other side, as for this, so the time side, what I have is I h bar 1 over f df dt equals E. And the solution of that is something that will look like this, f of t, which is f of 0, exponential minus ah bar of, I over h bar of et. And as you can see in the slide, in a more general way, E are the eigenvalues of the operator H, as we can see here. So I can generalize this to f of t equals f of 0 exponential minus h bar ht, where h now is the actual Hamiltonian operator. So at the end, what I have is a generic wave function, which will be this part so I removed the constant, I just put the constant in here, times the eigenvalues in space of the wave function that I need to find out through the time-independent Schrodinger equation. One thing you may ask is, say, well, hang on, we've got exponential of a matrix. How do I do that? Well, that's fine, because exponential of a matrix, I remind you that a matrix can be seen as an infinite sum of polynomials. So that would be an infinite sum of matrix with different powers, and that's fine, I can do that. So in a way, this is just a notation in a way. Right, and so message to take away is that we can actually reduce the general Schrodinger equation in most cases to this time-independent Schrodinger equation. And then we can look at different systems. The easiest one is the energy level of a free electron. So say you've got an electron in space and you just want to know what are his energy levels. So for that, you need to know his Hamiltonian. That's the first thing to do. In this case, as it's a free electron, it only has its kinetic energy. So kinetic energy is 1/2 of its mass times its speed, v squared. But if you remember, in quantum mechanics, I already mentioned that the speed v, velocity v, is actually not a good quantum operator. The good quantum operator equivalent to that is actually the momentum, p. And p, so the momentum in classical, the momentum in classical, so the momentum p in classical mechanics is m times v. So that means that the kinetic energy in quantum mechanics is the momentum squared divided by 2m. That's the first thing. And the second thing is that the momentum, so is an actual, in quantum mechanics, is an operator. And this operator has this form that can be derived, which is minus I h bar and derivative of, so in this case along x, derivative of x. And the most general case is that this operator p will be minus I h bar and the operator nabla, the vector operator nabla. So in fact here there should be a vector, it should be a vector as well. And the dot here and here means that this is an operator that doesn't make sense on its own. It has to be applied to something, to a wave function. And that's what we do in the Schrodinger equation. So we've got h psi equals e psi. So I can replace now the p squared by, if it's along x, by this expression, which is simply a second derivative in space, which, by the way, can also be the operator delta. So I can rewrite this in a second-order differential equation, which would be psi second, plus 2me divided by h bar squared psi. This equals 0. Solution of that are known. They're very easy. It's basically of this form, so sinusoid or exponential ikx, where k is a constant, which is the wave vector of propagation of this free electron along x, and is given by square root of 2me divided by h bar. If you just, so the k is actually this part here. So sorry, that's k squared. So solution of that is very easy. You've got a plane wave. So if you add the time dependent for the wave function, you've got a plane wave for a free electron with this associated energy, which in this case, so if I rewrite this, would be h bar squared k squared over 2m. And that p equals h bar k as well. So basically, what I'm saying is that the energy is p squared over 2m, which is, well, the standard kinetic energy of a particle, the classical one this time, the eigenvalues. Okay? This was, here we use the operator, so technically here it should be a hat actually, but we use the operator, p squared, and we end up with the way the eigenvalues, the result, the measurement that would be p squared over 2m. So that's the easiest example you can think of, and then you can go on to more complicated one of them being the hydrogen atom, which I already mentioned. So the hydrogen atom is the simplest atom you can think of. It's simply a proton interacting with an electron around it. So if I look at this Hamiltonian, I've got the kinetic energy part plus the potential energy part. The kinetic energy part we already saw, it will look like this. It's the same one as before, it hasn't changed. It's this part here. And this will never change. In fact, this is the kinetic energy term. Plus this term, which is the potential energy, which is basically the Coulomb potential interaction between the proton and the electron. Okay? Which will be E squared, the charge of the two, so E for one for proton, E for electron, divided by a constant times r squared, which is the distance between the proton and the electron. So if you try to resolve that, you end up with energy levels of this system which are quantized of this form. So they will be minus 13.6 divided by n squared, where n equals from 1 to 3, 4, and so on. And this is in actual electron volt. So to give you an idea of electron volts, so 1 electron volt is 1.6 10 to the minus 19 joules. Okay, so it's very, very low value. That's why we use the electron volt unit. And here is the diagram. So for n equals 1, you've got this 13.6 energy level. So that's the lowest energy level of the hydrogen atom. So it would be the so-called ground state, the closest. And then you've got n equals 2. So generally, so the Lyman series, Balmer series, Paschen series are so from the discoverers of the different photon emission from the various levels. So Lyman series for the level 1. The Balmer series was for level 2. So the value would be 13.6 divided by 4. So that's 3.4. So that's the second state. And then you've got angle 3, 4, 5, and so on until n goes to infinity, which is the energy tends to be 0. Of course, it's a convention. We could have taken the other way. But what we say is that basically what he's saying here is that when the electron is at the lowest level, it takes the energy of 13.6 electron volt to actually take away that electron from the proton. It's the ionization limit. So it's energy 0 because once the electron is on this sort of shell here, this sort of orbit here, this one, the outer one, then there is no more energy associated to it. It's got 0 energy because we just detached it from the interaction with the proton. So that's why we put the limit to 0. Okay? And then O below to the ground state, which is therefore minus 13.6 electron volt. And what you see here is the sort of planetary model that was developed by Niels Bohr, which kind of give a nice insight of the energy level of hydrogen atom. And he found this result using the planetary model, and fairly simple model, where the only assumption really made, and the only quantum assumption made is that, well, the hydrogen, for the hydrogen atom, the electron will have quantized energy levels. And with this, he showed that this energy level should look like this, which exactly matched the experimental observation by Lehman, Balmer, Paschen, and so on. So that is the so-called planetary model, which of course is wrong physically, but gives a good understanding of what it could look like, and specifically the right energy levels. But so he didn't actually. So this result found by Bohr was not through actually trying to solve the Schrodinger equation with this Hamiltonian, because if you do that, so you can do that. So if you try to develop this, you will find Eigen wave functions, Eigen vectors in this case, for the wave function, which will be psi of 3 coefficient NLM. And you will find two parts, a function that is only dependent with the radial, so the axis R, so the radial dependence R, so from here to the electron. And then another function, which we call the YLM function, which I call the spherical harmonics in mathematics, which are dependent on theta and phi, which are the two angles in spherical coordinates, and which would be the equivalent of latitude and longitude in this case. And here is the full version of this equation, which is rather complicated, with a lot of sums, a lot of various powers of polynomials, of angles and distance, and an exponential decay. That's very important, the exponential decay, though, as a function of time, because that's what allows you to say that physically the electron can be as far as possible from the proton, but at some point it's got to get out of it, and there is no more hydrogen atom. So you've got to have some spatial dependence and physically what happens is that the Coulomb interaction will die off at some point. Okay, the Coulomb interaction at the end of the day is on 1/r². Okay. So, but at least this is a perfect analytical solution of the Schrodinger equation for the hydrogen atom. Here I represented the various energy levels, so the 1s, 2s, 2px, 2py, 2pz, 3s, and so on and so forth. And what you see, these sort of nice donuts or spheres and various balls and so on, those are actually the construction of these wave functions as a function of the different coefficient N, L, M. And you can see how spatially the probability of finding the electron will look like as you go. So if I take the planetary model as I go away from the ground state, from the center of the hydrogen atom, and as I go away and on higher energy state. Okay, so you've got some sort of donut shapes and various shapes that gets more and more complicated. And that is because these wave functions are already way complicated. But at least you can analytically find that. And what's nice about it is that if you do that properly, so you find these solutions, and what you find for the energy levels are exactly the same one as Bohr found for his rather simpler planetary model. Okay, and this got to be probably the best coincidence ever, although it wasn't a coincidence, but it's got to be the best result between some simple model and some rather complete non-simple model. Okay. But what I want to point out here, and I again go back to the first lecture, is that this is a solution for the simplest atom that you can think of. One proton, one electron. And this is already extremely painful to find out. But at least it's analytical. As soon as you go on to helium atom, where you've got 2 protons, 2 electrons, and some neutrons, then that's it. There is no way you can have an analytical solution. you can find, you can barely find a computer solution. But then as you move on to lithium with 3 protons, 3 electrons, then that's it. There is no computer these days that can perfectly compute and gives you what these look like, what the energy state look like, and so on and so forth. Of course, as I said before, we've got some assumptions that we can make that works very well, where we can simplify the problems and eventually generalize the hydrogen atom to more atoms and have a good idea of what happens for bigger atoms, and even for molecules, which are made of atoms. But the fact is, there is no classical computer that can give us these solutions perfectly, but the quantum computer would. I say yet again back to the beginning, where to give an insight into why this is important. Just another model that is used a lot in quantum mechanics is actually used also in quantum technologies. In classical physics, is a rather simple solution, a rather simple problem, is the harmonic oscillator. In this case, we talk about a quantum harmonic oscillator. So we have, again, the kinetic energy, we have the potential energy. So in this case, the potential energy is 1/2 of kx squared, where k is a spring constant. And a harmonic oscillator can be a spring that you just pull and look at, look at it sort of bouncing off back and forth. It can also be the same potential will apply for a pendulum. It's the same thing as a harmonic oscillator. And so this is in classical physics. So in classical physics, another good example is a guitar. So some sound instrument would work. So you end up with the different harmonics, which are the different notes of your guitar. So one harmonic, second one, third, fourth, and so on. So this is how you make the various sounds. And this is classical, no problem. And then you can say, okay, well, now I can just apply this to Schrodinger equation, find the results. So you can solve that perfectly as well. And here is what the wave function look like. So the equivalent of that, really, in a way, where you have 1 bump and then 2 bumps, 3, 4, 5, and so on, as you go on. And what you see here is the energy levels associated to each of these wave functions for the quantum harmonic oscillator. And in this case, you can show that the energy levels are, again, quantized, no surprise, and that they look like this, which is n plus 1/2 h bar omega, where omega, in this case, is related to the classical version of the spring constant. And the classical case, in the quantum case, is the same. It's basically, say, how two atoms hold together through a common force. So you can mimic that with this harmonic oscillator and this quantum harmonic oscillator. By the way, if you want to, so you can solve perfectly those wave functions, and that's what they look like. So for the first order, second order, so 0 order, first order, second order, third, fourth, and so on. And you can see, although it's simpler than the hydrogen atom, but it also gets more and more complicated. But of course, what's more interesting on the Schrodinger equation is to solve it for some specific problems, which are, and we talked about it before, which are more sort of a two-state problem, because that's what quantum technology will be interested in. I erased it, but in order to have qubits. And the good example, as we talked about it before, is the spin, electron spin. So here I put back the original experiment of the so-called Stern-Gerlach experiment, which were done with silver atoms. So what they had is they had an oven with silver atoms, and they shoot atoms, silver atoms, out of this oven, and they put it in between a magnetic field through this North Pole and South Pole. Okay, and So I'm not going to go through the whole math, but you can show that so this spin. So if these silver atoms have spin, and that's what the result of the Stern and Gerlach experiment showed. But this spin, so if you put this spin, so it would be like a small magnet. This small magnet will interact with the magnetic field here in between the North and South Pole. So you would have an extra Hamiltonian term. So the potential energy term in this case would look like this, minus mu b, where b is the magnetic field, and mu is the associated so-called magnetic moment, or the small magnet associated to the spin of the silver atoms. And if you do that, you can associate a force, which would be, so that's the standard classical approach, which would be minus the gradient of the potential energy. And what you have is something that looks like mu of z, if I project along z, times the gradient of b. So what you have is, as a function of the gradient of b, you have different force applied to your silver atoms. And the prediction tells you that you have this sort of continuously varying forces on those atoms, and you have this spread of the atoms onto a screen at the end. But the observation by Stern and Gerlach was that there was no such thing. What there were instead is there were only two spots. Okay? So the force was not uniformly distributed as a function of the gradient of the magnetic field in between the North and South Pole. Something else was up. What is something else is the fact that the spin associated to the silver atoms, or to the outer electron of the silver atoms, so the spin Sz is actually quantized. It can only take two values. So when the interaction goes with the magnetic field, so you can transform that into this expression, which is some coefficient, and then the scalar product of B, and this observable now, S, which is the spin state of the electron. This spin state has only two values, plus or minus h bar over 2. And that's why Stern and Gerlach only observed two spots rather than a continuous spot that classical mechanics was predicting. So what you have is now you have so here is just a total view. So you have the silver atoms, you have an orbital angular momentum, and you have a spin momentum of the electron. So in this case, this is what you observe, these two states, where S equals minus half, and the MS is minus half, or is 1/2. It's minus 1/2 or plus 1/2, which were the, they should be, no, that's right, which were the two eigenvalues of the operator Sz, the spin operator of the electron. And now we can go back to the operator Sz, the matrix associated to the operator Sz, which is the Hamiltonian H, observable Hamiltonian Hs, which is this interaction, which is this interaction between the B field and the spin of this small magnet, which is the electron. I can write it, so it would be ms h bar omega 0, where ms can take two values. So this matrix can be written as a 2x2 matrix, because there are only two values, two eigenvalues, which is plus h bar over 2 and minus h bar over 2. And this matrix, I can rewrite it as we saw before, the Pauli Z matrix, where you have so 1 plus 1 as a value, or minus 1 as a value. And then I can have, and we did that before, I just put back what I put before, is that Sz will have two eigenvectors associated to these two eigenvalues, so we can call them up or down for the spin, the two states of the spin, forming an orthogonal basis, because if you're in an up state, you're not in the down state, and if you're in the down state, you cannot be in the up state. So the scalar product between these two eigenvectors is 0, or the inner product. And if I apply Sz to plus, I've got h bar over 2 plus, or up, sorry. And if I apply Sz onto down, I've got minus h bar over 2 down. And of course, this is the most general wave function for an electron spin, would be a superposition of the two, which, if you remember, we called 1 and 0. So what I wanted to show you here is that, so at the end of the day, quantum technology is based on quantum physics, of course, but you can see that you don't actually need to worry too much about all of those in a way for quantum technologies. You just need to have a starting point. In this case, it's nice to know that you have quantized energy, because some other systems maybe will use the qubit as a level 1 and level 2. Right? So you can say, and in fact, that's what people do when they trap atoms and use it as a qubits. What they do is they can play a clever trick using lasers and trapping lasers and also exciting lasers, where they can put the qubit in a superposition. So in this case, it would be the energy level of the atom in a superposition state between n equals 1 and n equals 2. So that would be the qubit. The qubit in their case would be, well, I can be in n equals 1 state or n equals 2 state, and I can be in one or the other in superposition of the two. So it's nice to know that the hydrogen atom has quantized levels, and we know them, but in a way, we don't actually care about how to find them, as long as they do exist. And it's the same for the quantum harmonic oscillators, which is basically what is used in superconducting qubits, with a bit more ingredients than that, because you can see here that if you take, say, this level and this level as a qubit, you have a problem, because to differentiate this one from this one, for instance, is impossible in terms of energy, because they have the same energy. So superconducting qubits, as you will see in quantum technology lecture, you have to add a trick, but roughly the idea is the same, is that you identify two energy levels to be your qubit, and you try to put these two states in a superposition state to form your qubit, of being on this energy level or this energy level. And so on and so forth. So this one we've seen before is the spin. So this is a bit more, this is clearer in a way, because, well, you have this property which is either up or down, blue or red, and that's good enough for our qubit. And with this, I will, with this, I will conclude this part, and we'll stop for today. So we will have the 4 other lectures, like I said, so it won't be me. Hopefully, we will keep the planning as we have it. And then, I suppose for me, that's it for this year. There will be the lectures next year, for sure. We'll do them again. And of course, they will be improved. It can only be improved. Or you can always do worse, but that's not the idea. And we'll see how that goes. And with that, I thank you and see you next year for me. Thank you.